Jackson. In this video we're going to start looking at the chain rule. In our last video we reviewed what we meant by composition of functions, and the chain rule, another name for it could be the composition rule or the substitution rule. Official name is the chain rule for derivatives, but it could be called the composition rule because we're doing the derivative of a composition. So we're taking the derivative of the composition of functions f and g. The derivative of f composed g of x, or in other words, the derivative of f of g of x. What you do is you do f prime, but evaluate it at g of x, then times g prime of x. Or the way I really like to think of this is as the substitution rule, because you take your function, which is originally in terms of x, you do a substitution where u is g of x, and you replace this so this now is the derivative of u, but with respect to x. Well, what you do is you take the derivative of f with respect to u, f prime of u, but then you have to multiply by the derivative of the u. In other words, the derivative of the g. Notice that this f prime is evaluated at u, which is the g of x. In completely Leibniz notation, this is df over dx is df over du times du over dx. So we're going to look at that. As I said last video, we talked about this part here of the notes where we're talking about composition of functions. But let's look at linear functions, what happens. So we'll start with linear functions for a couple reasons. Number one, we know very easily what their derivatives are, and their graphs are really simple, so it's a kind of a simple case. And since the derivatives are constant, that makes things a lot easier to work with. And also, because the formulas are easy, it's real easy to do the composition. So we'll let f of x equal m sub f x plus b sub f. And so then its derivative is the constant function m sub f. Now remember, m sub f, b sub f, m sub g, and b sub g are constants. Similarly, let g of x be m sub g of x plus b sub g. Take the derivative, you get g prime of x is just m sub g. Of course, those are just the slopes of those two lines. F composed g of x is f of g of x. So you take the formula for f of x, m sub f of x plus b of x, b sub f, and where the x is, you replace with the parentheses and put in there, well, what's in this parentheses? G of x. G of x is mg x plus b sub g, so you put that in there. Now we're just using the distributive property to multiply both of these terms by m sub f. And so you get m sub f times m sub g times x plus m sub f times b sub g plus b sub f. And those are all constants. So if you look, this is just a constant times x plus another constant. And so the coefficient of the x is the slope here. So the derivative of this composition function is just the product of the two original slopes. That's the product of the two original derivatives, f prime times g prime. So we see that the derivative here is going to be the product of a couple of derivatives. And we can see this with a couple of different activities. Here's a link to an activity that Doug Davis wrote in Geogebra. And let me get to that one here. Here's what it looks like. And we see we can control the slope and y-intercept here, the coefficients here on g of x, and then we can do the coefficient here of f of g or f of u, g is the same difference. So it's a coefficient times g plus the y-intercept here. Both of these cases, the y-intercept, this one's -1 and this one's 1. Okay, so let's take a look at that. We can see the graphs here. We can start by just showing the two original graphs. And notice we can kind of get to the output this way. Start with an input here, which we can control with the slider. And from there, we go up to the original function, which is the inner one, g, and get an output. The output there becomes an input here. So this x is the same as this y. So we're just reflecting this point over the line y equals x to get here. So this vertical distance and this horizontal distance are the same. Then we go up to the function f of g, because this is a G value here as the input, and then the output comes across here, and that gives us the Y. Now what we want to do now is actually take that and bring that same Y back over the original X to get the output of the function here, which is F composed G. And so we can see that happens as we go along here. Now what about the slopes? Well, the derivatives are just the slopes of these lines, so that works out real nicely. The derivative of this one here, of course, we know is just the derivative of is the coefficient here, which is 0.5. So that's given right here. And then the derivative of this, the outer function, is 1.5. That's given here. And it turns out if you just multiply those two together, half of 1.5 is 0.75, and that turns out to be the slope here, as we just proved algebraically a while ago, but you can see it here. And you can explain this and experiment with different values of the slopes here and different values of the x here. One more thing that this does is shows you what happens when we're thinking about sort of that difference quotient level. So we move over by some value of h, which you can control here. And we have a difference between x and x plus h, and then it gives us this length, and then it also gives us an interval here from x to x plus h. That interval is mapped by this first function into this horizontal, brought over to this, it's a horizontal interval here, it's mapped onto a vertical interval here. We take that's an interval for g. We take that and flip it down here, and that becomes the input for the next part is this interval, and that's mapped by f into this horizontal, to this vertical interval here. And that's the vertical interval that we started with. So ultimately, on the composition function, we're mapping this interval into the one here. And that may help you see what's going on there just a little bit. Here's the exact same composition of functions illustrated using my Geogebra app. The outer function is 1.5u plus 1. The inner is 0.5x plus 1. This time, instead of putting this graph on the original, I'm putting it over here in the u-y plane. So here again, it's the same thing. Here's the x value is controlled by this slider. So here, if we I can move it this way as 2. For example, we move it to 3. We have an input of 3 here, and it goes up. Now the tangent lines are the original lines, so we can look at the slopes there. The slopes here are 1/2 and 1.5, and we multiply those to get the 0.75, as you can see here. And so this gives you the same same conclusion that we had there in the other app. Okay. So we're going to go on and take this and this my app and look at some things where they're not linear functions, but I think we'll start that on the next video. Come back for that.